The basics of an ideal gas. Basics of an ideal gas. An ideal gas is as follows. Ideal gas assumes a couple things. Ideal gas assumes no volume, that a gas is essentially a point of charge. Whatever the container it's filling, the gas is not really taking up any of that space. It assumes no interactions. It assumes each gas is just like a marble that's bouncing around. Unlike it's like two billiard balls. That instead of, there's no chance that a gas will hit another gas and stick. And it assumes it's always a gas. Always a gas. So it doesn't matter what temperature you're at, it's going to remain a gas. None of these things can be truthfully true because gas will take up some space. Gas will have some interaction. You're going to have chemical reactions. And gases, when you cool them down enough, they will turn liquid. You can liquefy oxygen. You can liquefy nitrogen. You've heard of liquid nitrogen. It's that stuff people like to play around with. They freeze objects in liquid nitrogen and you throw them against the wall and they shatter. But we have certain equations that will relate that. The main equation is PV equals nRT. The idea that pressure, volume equals moles, R gas constant T. The R gas constant, I decide, depends on your units of pressure, but it's either usually ATM liters per mole Kelvin or bar liters per mole Kelvin. Those are the most common ones. However, those usually don't make too big of a difference in your numbers. The beauty of this is, even if you're only given two values, as long as the other values are held constant, you can look at another situation. So you can write several equations from here. You could just use this guy, but you could also say P1V1 equals P2V2, because if the moles of gas and the temperature of gas are kept the same, we can look at that. If I say gas at 1 atmosphere has 13-liter volume, and I increase the pressure to 21 atmospheres, what is the volume? This one, we don't need R, we don't need anything else. We'll just say 1 times 13 equals 21 times V. How would we solve for that? We just divide both sides by 21. You get the volume has shrunk from 13 liters to 0.619 liters. We could have something like, if I have a gas, if we use the PV equals nRT, just normally gas at 2 bar and 333 Kelvin. Let's see. We'll say 1 mole gas. 1 mole gas at 2 bar, 333 Kelvin. What is volume? So you're rearranging this to solve for volume. So you'd say V equals nRT divided by P. N is 1. R is our 0.08314 bar liter mole Kelvin. Temperature is 333 Kelvin. And our pressure is 2 bar. Setting this up. Bar, mole, Kelvin, Kelvin. Our units are liters. So 0.08314 times 333 divided by 2. The volume is 13.8 liters. 13.8 liters. Simple enough to calculate. One other major thing you could do with this, real quick, before we run out of time, is look at density. Because density is a mass over volume, you could rearrange the ideal gas equation so that density is equal to pressure over RT times a molar mass. So given a density of grams per liter, you could find the molar mass, or given a molar mass, you could find the density. Because what we're essentially saying is mass over volume equals moles times molar mass over volume, which is why we can say N over V equals P over RT. So to do both sides, we have to multiply by the molar mass. So if I have we'll just say common gas. We'll use a common gas. We'll use propane, C3H8, at, let's say, three atmospheres and 298. 298. What would the density be? What would the density be? Well, the molar mass would be 12 times 3 plus 1 times 8. So 36 plus 8 is 44. So we'd say 3 times 44 divided by our 0.08206 and times our 298. So under these conditions, propane would have the following density. Would have a density of 5.4 grams per liter. 5.4 grams per liter. But that's an easy thing we can do with the ideal gas equation.